Hey guys, this is Elena Seungeun Lee from We Learn to Share. Welcome to the video of linear algebra. Well, in this video, we're going to uncover the significance of solution sets in linear systems and dive into how to find them. Well, let's first go with the definition. So what does it mean to be homogeneous? So homogeneous is said to be homogeneous if an equation could be written in the form of ax equals 0. So this means if you put this in a matrix system, in a augmented matrix form, you will have all these coefficients over here in the results over here, right? But all of the numbers in this place will all be 0, 0, 0. So it's equal 0, right? So you should always remember that if there is 0 all over here, then that will be the homogeneous system. To put that into more definite terms, it would be when A is an m times n matrix, and then 0 is the 0 vector, right? A vector that has all zeros in Rn. And such a system ax equals 0, it's important to remember that they always have at least one solution. And that would be what? That would be a 0 vector, right? Because if you put 0 in any of the x's and solve this, you will always have a 0, right? So that means that a homogeneous system always have at least one solution, namely x equals 0, right? The 0 vector in Rn. And this 0 solution, we're going to call this trivial solution because it doesn't really mean anything, right? So if anything is a trivial solution, it means that the solution is 0. And if it's a non-trivial solution, it's everything else that is other than 0, right? So the important question is whether there exists a non-trivial solution for the given equation ax equals 0. That is, a non-zero vector x that satisfies ax equals 0. And there is a theorem, existence and uniqueness theorem in section 1.2, theorem 2, that leads immediately to the following fact, that the homogeneous equation ax equals 0 always has, has a non-trivial solution, might have a non-trivial solution, if and only if the equation has at least one free variable. Okay. So this is important. If it has at least one free variable, then this would make ax equals 0 to have a non-trivial solution. Well, let's remember what was a free variable. So if there was a number like, let's say that we had like 0, 0, 0, 0, like in the echelon form. Okay, let's find out a better example. Like this, right? In this equation, you'll have x3 as your free variable. And the thing is that you can express the other variables, for example, x2 and x1, which is a basic variable, so not a free variable. You can write that x2 equals 2. And you can also write that x1 plus 2x2 plus 3x3 equals 4. And you can substitute this into here, and you can substitute this value into here, and then you'll put all of that to the other side. So 4 minus 2x2 minus 3x3. And that means that you can actually you can write x1, the basic variable, a non-trivial solution in the form of x3. And other free variables. So you can only remember that ax equals 0 homogeneous equation has a non-trivial solution if and only if there is at least one free variable, because according to these free variables, you can compute and you can put and substitute any values to make it non-zero. Now let's look at some examples, right? So that it can make it even more clear. Let's say that you have this system of 3 equations. So determine if the following homogeneous systems has a non-trivial solution and describe the solution set. So again, non-trivial solution means solution that is not a 0 vector, that is not a 0, right? So let's first put these 3 equations into into the matrix form. So let's put 3, 5, minus 4, 0. We have minus 3, minus 2, 4, 0. We have 6, 1, minus 8, and 0. So what you can do is to reduce this into an echelon form. So you can see that you can basically add R1 plus R2 to eliminate this into 0. And also you can multiply R1 times minus 2 and then add that into R3 in order to eliminate this into 0. So let's do that. if you add R1 and R2 together, you will have R1 stay the same, and then you have 0, 3, 0, 0, right? And if you times minus 2 to the R1, you would have minus 6, minus 10, 8, 0. And if you add that to R3, it would be 0, minus 9, 0, and 0, right? Okay, so in this form, you can see that this is 3 times the second one. So if you do that again, then if you do R2 times 3 plus R3, then you would have 3, 5 minus 4, 0, 0, 3, 0, 0, and 0, 0, 0, 0, right? So in this case, you can see that this means that x3 is a free variable, right? X3 is a free variable. And again, because you have one free variable, that means that this has a non-trivial solution, because anything you can see, for example, in the row 1, you can substitute any value into the free variable to make the non-zero form. So that means that if you do all this again, so if you put this into a reduced echelon form, then you can see this as you can divide row 2 by 3, so it will be like this. And then you could divide the first row also to 3. So you can have 1, 5 over 3. You can have minus 3 over 4 over 3, and you can have 0. And, well, in this form, you can see that you can also you can multiply minus 3 over 4 to the second row to reduce and add this with 1. So you can have 1, 0, minus 4 over 3, 0, and 0, 0, 0, 0. Not 0, 0, 0. You can have 0, 1, 0, 0, 0, 0, 0, 0, right? In this form, let's now put this into equations. So this means that coefficient of x1 in row 1 is x1, right? And then you can have minus 4 over 3, x3 equals 0, and x2 equals 0. And x3 is a free variable, right? So this is 0 equals 0. And if you solve for the basic variables x1 and x2 to obtain x1, you can put this over here. So that will be x1 equals 4 over 3, x3. And that's all, right? So if you put that into a general solution of ax equals 0 form, a general solution form, you would have x equals x1, x2, x3, meaning that you can put in this thing in x1. So that's 4 over 3, x3, and you can have 0 over here. And x3 is free, so you put this in the same form. And if you pull out x3 out, then you would have 4 over 3, you can have 1, and you can have 0, and you will have 1. And this basically means that if you would add this over here, add this over here, add this over here, which makes it same to this one. And then, so this means that x3 is some kind of v, and this, where v is, the vector is like this. So this means that x3 is factored out of the expression for the general solution vector, and this shows that every solution of ax equals 0 in this case is a scalar multiple of this vector v. So this means that this trivial solution is obtained by choosing x3 to be 0. So if you put x3, the free variable, as 0, then of course this would be equal to 0, right? But in its case, if you put in like 1 to x3, because you can do that because of free variable, then that won't equal a trivial solution. Or if you put it to like 5, of course it will not be a trivial solution. So in this way, you can see how a free variable x3, by substituting any kind of value you want into x3, you can make the equation to have a non-zero solution. So this is how you can basically explain this concept. If you have one free variable, you can substitute anything to the variable which makes ax equals 0 to have a non-trivial solution. Okay, now let's solve another example to make this more clear. In this question, it's saying a single linear equation can be treated as a very simple system of equations. Describe all solutions of the homogeneous system. And we have 10x1 minus 3x2 minus 2x3 equals 0. And don't be surprised, because yes, this is the end of the question. You don't have 2 or 3 equations, but you have only one equation. In this case, what you can do is just solve for the basic variable x1 in terms of free variables, what we have always done. Okay, so in this case, you can just divide 10 into other coefficients. So if you divide 10 to make this coefficient, first coefficient of x1 into 1, then it would be basically x1 minus 0.3 x2 minus 0.2 x3 equals 0. And if you put this into the general solution form, then you would have x1 equals 0.x2 plus 0.2 x3, right? And x2 and x3 would basically be free variables, right? So as a vector, the general solution is like this. And you have x1 as being 0.3 x2 plus 0.2 x3. You can have this as x2, x3 being free variables. And this means that you can put the variables that are related to x2 into one part, and then you can add that into another form that only has something related to x3, right? So I'll show you how to do that. So first, you can put on everything that has something related to x2. So you can put 0.3 x2. You can put x2. You can have 0. And you can add that with 0.2 x3, and because there's nothing over here related to x3, you can put this as 0. You can have x3 over here. And again, you can pull out x2 into the front, x3 into the front. So let's do that. So if you do that, you have x2 out here, you can have 0.3, 1, and 0. And for here, you can have x3 pulled out, we'll have 0.2, 0, and 1 over here. So this means that over here, this could be described as some vector u, and this to be something vectors v, where x2 and x3 is free. So this calculation shows that every solution of this one is a linear combination of the vectors u and v over here, right? A scalar multiple of this. That is another thing to say that the solution set spans u equals v, because that was what means to be a linear combination of vectors u and v, right? And since neither u nor v is a scalar multiple of the other, this is said that the solution set is a plane through the origin. So if you draw this, you would have something like this is x1, x2. You would have some parallelogram shaped solution. So this being v, this u, and then you'll have x3 sitting over here, right? Okay, and examples 1 and 2, along with the exercises, what we have solved for today, illustrate the fact that the solution set of a homogeneous equation ax equals 0 can be always expressed explicitly as spanning v1 to vp for suitable vectors v1 to vp. If the only solution is a zero vector, then the solution set, so if it only has a trivial solution, the zero vector, then the solution set would span 0, right? And if the ax equals 0 only has one free variable, all right, like this, so this is like only zero vector as answer, then the solution set will span 0, and if it has only one free variable, then the solution set is a line through the origin, like this, and a plane through, so this is a line through the origin, but if it has 2 or more free variables, then it becomes something like this, like a plane, right? A plane through the origin. Note, however, that a similar figure could be used to visualize span u, comma v, even when u or v do not arise as solutions at ax equals 0, and we will learn that soon. So, okay, in today's video, we've learned about some parts, the first part of the solution sets of linear systems. I hope this video has helped you understand a little bit more of linear algebra. If you enjoyed this video, please subscribe to our channel and press the like button. Thank you for watching, and see you in the next video.